heapq. Heapq. Heapq algorithm. Heapq.py. This module provides an implementation of the heapq algorithm, also known as the priority queue algorithm. Heaps are binary trees for which every parent node has a value less than or equal to any of its children. This implementation uses arrays for which heap k less than equal to heap 2 into k plus 1 and heap k less than equal to heap 2 into k plus 2 for all k counting elements from 0. For the sake of comparison, non-existing elements are considered to be infinite. The interesting property of a heap is that its smallest element is always the root, heap 0. The API below differs from textbook heap algorithms in two aspects. We use zero-based indexing. This makes the relationship between the index for a node and the indexes for its children slightly less obvious, but is more suitable since Python uses zero-based indexing. B. Our loop method returns the smallest item, not the largest, called a mean heap in textbooks, and max heap is more common in text because of its suitability for in-place string. These two make it possible to view the heap as a regular Python list without surprises. Heap 0 is the smallest item and heap.sort maintains the heap invariants. To create a heap, use a list initialized to empty list, or you can transform a populated list into a heap via function heapify. The following functions are provided. heapq.heap push heap item, push the value item onto the heap maintaining the heap invariant. heapq heap pop heap pop and return the smallest item from the heap maintaining the heap invariant. If the heap is empty, index error is raised. To access the smallest item without popping it, use heap 0. heapq heap push pop heap push pop heap item, push item on the heap, then pop and return the smallest item from the heap. The combined action runs more efficiently than heap push, followed by a separate call to heap pop. heapq.heapify x transform list x into heap in place in linear time. heapq heap replace heap item, pop and return the smallest item from the heap, and also push the new item. The heap size doesn't change. If the heap is empty, index error is raised. This one step operation is more efficient than heap pop followed by heap push and can be more appropriate when using a fixed size heap. The pop push combination always returns an element from the heap and replaces it with the item. The value returned may be larger than the item added. If is not desired, consider using heap push pop instead. Its push pop combination returns the smaller of the two values, leaving the larger value on the heap. The module also offers three general purpose functions based on the heaps. Heap.merge iterables, key, reverse is equal to force. Merge multiple sorted inputs into a single sorted output. For example, merge timestamped entries from multiple log files returns an iterator over the sorted values. Similar to sorted itr tools chain pointer iterables, but returns an iterable, does not pull the data into memory all at once and assumes that each of the input streams is already sorted smallest to largest, has two optional arguments which must be specified as keyword arguments. Key specifies a key function of one argument that is used to extract a comparison key from each input element. The default value is none. Compare the elements directly. Reverse is a boolean variable. If set to true, then the input elements are merged as if the comparison were reversed. To achieve behavior similar to sorted iter tools.chain pointer iters reverse is equal to true. All iterables must be sorted from largest to smallest. heapq.n largest, n iterable key is equal to none. Return a list with n largest elements from the dataset defined by iterable key. If provided, specifies a function of one argument that is used to extract a comparison key from each element in iterable. For example, key is equal to str dot lower equivalent to sorted iterable key is equal to key reverse is equal to true and heap q n smallest n iterable key is equal to none. Return a list with n smallest elements from the data set defined by iterable key if provided specifies a function of one argument that is used to extract a comparison key from each element in iterable. For example, key is equal to str dot lower equivalent to sorted iterables key is equal to key n. The later two functions perform best for smallest values of n. For largest value, it is more efficient to use the sorted function. Also, when n is equal to 1, it is more efficient to use the built-in mean and max function. If repeated usage of these functions is required, consider turning the iterable into an actual heap. Basic example. A heap sort can be implemented by pushing all values onto a heap and then popping off the smallest values one at a time. Diff heap sort iterable h is equal to blank for value in iterable heap push h value. Return heap pop h for I in range length h. Heap short 13579246800 01234567 heap q directory. Okay, let's do inside the collection heap q. Heap q example example from import heap push import this now from heap q import start heap short print. Okay, print heap short is equal to result and print result 012. It's a sorted form. This is similar to sorted iterable, but unlike sorted, this implementation is not stable. Heap elements can be tuples. This is useful for assigning comparison values such as task priorities alongside the main record being tracked. H is equal to empty h example 2. From heap q import star heap pop print heap pop he push h 5 comma write code he push h7 release product he push 1 write spec he push 3 he poop dot he pop dot protect print heap h dot heap h dot sort one write spec heap sort heap short list h short. Okay, need to provide this one as well. Hip short h 1357. One right is correct. And if I print only h, then what will be the output? 1357. Okay. Priority queue implementation notes. A priority key is a common use for a heap, and it presents several implementation challenges. Sort stability. How do you get two tasks with equal priorities to be written in the order they were originally added? Tuple comparison breaks for priority, task pairs if the priorities are equal and the tasks do not have a default comparison order. If the priority of task changes, how do you move it to a new position in the heap? Or if a pending task needs to be deleted, how do you find it and remove it from the queue? A solution to the first two challenges is to store entries as three tuple list including the priority, an entry count and the task. The entry count serves as a tiebreaker so that two tasks with the same priority are returned in the order they were added. And since no two entry counts are same, the tuple comparison will never attempt to directly compare two tasks. Another solution to the problem of non-comparable task is to create a wrapper class that ignores the task item and only compares the priority field. From data classes import data class, field. From typing import any. Data class order is equal to true. Class prioritize item, priority integer item, any is equal to field comparable, compare false. The remaining challenges revolve around finding a pending task and making changes to its priority or removing it entirely. Finding a task can be done with a dictionary pointing to an entry in the queue. Removing the entry or changing its priority is more difficult because it would break the heap structure invariance. So, a possible solution is to mark the entry as removed and add a new entry with the revised priority. PQ, list of entries arranged in heap. Entry finder, this a mapping of tasks of entries. Removed is equal to removed task. Counter is equal to iter tools count. Diff add task priority is equal to 0. Add a new task or update the priority of an existing task. If task in entry finder, remove underscore task count is equal to next counter entry is equal to priority count task. Entry finder task entry heap push pq entry. Diff remove task mark an existing task as removed. Raise key error if not found. Entry is equal to entry finder dot pop task entry minus 1 removed. Depop task, remove and return the lowest priority task. Raise key error if empty. When PQ priority, count, task. Heap Q, heap pop PQ. If task is not removed, delete entry underscore finder task, return task. Raise key error, pop from an empty list. Theory. Heaps are arrays for which ak less than equal to a2 into k plus 1 and ak less than equal to a2 into k plus 2 for all k, counting elements from 0. For the sake of comparison, non-existing elements are considered to be infinite. The interesting property of a heap is that a0 is always its smallest element. The strange invariant above is meant to be an efficient memory representation for a tournament. The numbers below are k, not a of k. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. In the tree above, each cell k is topping 2 into k plus 1 and 2 into k plus 2 in a usual binary tournament we see in sports. Each cell is the winner over the two cells it tops. and we can trace the winner down the tree to see all opponents he had. However, in many computer applications of such tournaments, we do not need to trace the history of a winner. To be more memory efficient, when a winner is prompted, we try to replace it by something else at a lower level. And the rule becomes that the cell and the two cells it tops contains three different items, but the top cell wins over the two topped cells. If the heap invariant is protected at all time, index 0 is clearly the overall winner. The smallest algorithmic way to remove it and find the next winner is to move some loser. Let's say cell 30, cell 30 in the diagram above into the 0 position, and then per percolate this new 0 down the tree, exchanging values until the invariant is re-established. This is clearly logarithmic on the total number of items in the tree. By iterating over all items, you get an O n log n short. A nice feature of this sort is that you can efficiently insert new items while the sort is going on, provided that the inserted items are not better than the last zeroth element you extracted. This is especially useful in simulation context where the three dots three holds all incoming events and the win condition means the smallest scheduled time. When an event schedules other events for execution, they are scheduled into the future so they can easily go into the heap. So, a heap is a good structure for implementing schedulers. This is what I used for my MIDI sequencer. Various structures for implementing schedulers have been extensively studied, and heaps are good for this as they are reasonably speedy. The speed is almost constant, and the worst case is not much different than the average case. However, there are other representations which are more efficient overall, yet the worst cases might be terrible. Heaps are also very useful in big disk sorts. You most probably all know that a big sort implies producing runs which are pre-sorted sequences whose size is usually related to the amount of CPU memory, followed by a merging passes for these runs, which merging is often very cleverly organized. It is very important that this initial sort produces the longest runs possible. Tournaments are a good way to achieve that. If using all the memory available to hold a tournament, you replace and percolate items that happen to feed the current run. You will probably runs which are twice the size of the memory for random input and much better for input fuzzily order. Moreover, if you output the zeroth item on disk and get an input which may not fit in the current tournament because the value wins over the last output value, it cannot fit in the heap. So the size of the heap decreases. The freed memory could be cleverly reused immediately for progressively building a second heap, which grows at exactly the same rate the first heap is melting. When the first heap completely vanishes, you switch heaps and start a new run. Clever and quite effective. In a word, heaps are useful memory structures to know. I use them in a few applications and I think it is good to keep a heap module around. Thank you.